So there we are. Hello everyone who is there. Today we have a very special webinar. We also have very special guests with us. Let me introduce you to Michael Lewis. I hope I pronounced this very difficult German surname correct. This webinar will be on a wonderful tool called Turbo Satori, which Michael has been working for many years now. We think it's really a good tool to combine with NIRx measurements. It's a real-time analysis program for fNIRS measurements. And with this, I will invite Michael to tell us more about this.
Thank you. Thank you for the nice introduction. So welcome, everybody. We would like to start with a short live demonstration of the software. So what you need to set it up and what you need to run it. And for this, we first will set up basically with our participant one example experiment, run NIRx to record the data, and I will share my screen so that you can see how Turbo Satori is used to connect to NIRx and to analyze the data. Afterwards, I will show you how the interface is set up, how the components work together, and show you some example data. And at the end of the talk, I will give a short presentation about the processing workflow and some of the statistical processing, as well as neurofeedback and BCI setups, and some outlook and some support cases, how you could reach us and how you could get support from us.
Great. Okay. So let me put on this tab. On this tab, I have a 8/8 motor montage. So we'll try to run a small finger tapping experiment and should be able to see how Turbo Satori works.
Could you set up the presentation?
Yes.
Thank you.
Let me have Michael share his screen. Okay, there we are.
Great, thank you. So Turbo Satori comes with two separate applications. One is the real-time software Turbo Satori, and one is the Turbo Satori Simul mode, which can be used to reanalyze data that was already recorded. So right now we use the normal Turbo Satori in the real-time mode. So the current version, which is still in development, is version 1.4. And this is the basic user interface. For now, I will just use it as to show you how straightforward it is to be used. First, I go to the top right and click on Connect. Now, Turbo Satori tries to search for open LSL streams, so nearest applications that are running. It found this application, and now I can just select it and click on OK. Okay, now I see that I'm connected. I see the channels and the streams. And as soon as I'm connected, I can basically hand over or go to NIRx and start the recording, which we will now
So I'm a rather difficult subject, and we have a lot of lights in this room. So some of the channels might not have very good signal quality, but nonetheless, for this webinar, I think we are good to go. So I'm streaming now.
What you can see is that now the data is coming in. You see that there's this moving bar. And what we can see as well is the setup that is used. So here we have this 8x8 setup here. And we can now, for example, select a channel and look at the signal. He will now start a NIRstim to show a basic design. So NIRstim is used to trigger specific information. Here we see the oxygenated time course and in blue the deoxygenated time course.
2, 3.
As you can hear, now the condition left is started, and maybe it's trying to start with the finger tapping. As you can also see, the signal seems to go up. Here on the right, we see the event-related average of this signal, and this is updated per condition, which we see here in the bottom left. As soon as there's another condition, like now, there will be here a second condition and a second color coding here as well. So each time there will be a new trial. This will be updated here in the event-related averages as well. And this allows you to see in real time the event-related average of multiple trials, for example. As a quality measure, we can see here in the bottom right the amount of channels that have a visible heartbeat. At the moment, it's, as Mahib said, it's not such a good setup, so we see that only 35% of the channels have a proper heartbeat detected. So this should be improved in the setup. But this is also shown here on the left in the channel selection table, where you see these little icons, these little heartbeat symbols. So if a heartbeat is detected in this channel, so meaning that the signal quality is good, there will be a little heartbeat icon shown here. Now, after some trials, you can see already a cleaner pattern for the event-related averages, and you can decide on which one you want to look at. We can already see that there seems to be a clear time when maybe starting with the task and when he's trying to stop with the task. As soon as we stop the recording in NIRx, we will also see that the recording will be stopped here in Turbo Satori. And this is the last trial, so we will shortly wait till this trial is over. Okay. Can you stop the recording now?
Mm-hmm. I'm stopping now.
Yes. So we saw that now no data is coming in, and it now finished the recording, and the data is basically here on the software.
Mm-hmm.
Okay, this is all you need to know. Now this experiment is over, and we can basically connect again to NIRx to start another experiment if you want to. Okay, if we want to reanalyze some data that we have recorded before, we can use the Turbo Satori simul mode. And this I will also use from now on to show what is possible with Turbo Satori and how you can use it. First of all,
I can disappear from the camera, right?
yes.
There you have it.
First of all, I want to show the main interface. So Turbo Satori is divided into different parts, and first let's start with the main interface. So this interface, as you saw, consists of 3 different plots. One is the channel selection plot, then we have the event-related average, and the overall channel selection. These plots can be freely adjusted in size, so that you can really focus on the information that you're interested in, and you can combine them as well in the form that you want to. Now, if you want to reload the data set, we have to look here into the real-time and analysis setup. So the button that was before in Connect is now Start. I make it bigger to see a bit more, I hope. If you click Start Simulation Mode, you will have the option to select the NIRx header file that you just used. Here I use a data set which we recorded previously, just for as an example. The SRI is the Turbo Satori and Satori format, which is generated automatically. So you only need the header, just need to select it and press Open. Okay, now it will load the data, and it will read it in the speed that it was recorded using NIRx. This you can see here. So this widget here in the top allows you to set some plotting settings, some network settings, and analysis settings. Now, I basically just stop this simulation to show you what this interface allows you. In this part, the analysis settings, you can define the event-related average time. So here, after the onset, we say that we want to have a 35-second period for the event-related average and a 5-second period before the onset of the trial. This part defines the length of the baseline, which is used to calculate the oxygenation concentration, or the hemoglobin concentration. Here in the plot settings, we can define the oxy, and deoxy time course as well as total, or we can also select the HRF, so the hemodynamic resource function of our model that we use for the statistics. But this I will explain later on, so we hide them for now. Okay, so if I open this data set, it will automatically start to run it. And if I select a channel here, as I said, I can see that this time course is showing up here. Now, after I've set up these things, I want to do some pre-processing. Here in this part of the bar, of the interface, we see some pre-processing options. Here in the top, it's all about the raw signal, which we don't care at the moment. We focus more on on this area, which is the pre-processing for the HPO, HP, and total. Now we have different options: a linear detrend, filtering, and motion correction, as well as SSR and channel subtraction. The SSR is only available if you have short channels connected to your device. Right now, we use the Butterworth filter, and we have the low-pass filter enabled with 0.2 Hertz, and a high-pass filter enabled with 0.01 Hertz. You could also change the filter to one of these. I will show the list later on. This can be freely adapted and can also be combined in different ways. The correction methods that are shown here are applied in the order. So first linear detrending, then the filtering, then the motion correction, SSR, and channel subtraction if wanted. In the bottom of this tab, we see that there is a sampling rate displayed, the time that we see the data right now, and the data package that is read in. As I said already, the heartbeat information can be seen here. And in this data set, we had a pretty good data quality, which is also visible here in this display. You see these little moving bars here. Every time you see a moving animated bar, it means that there was a heartbeat detected in this channel. In this case, we see that for all channels, we have a proper heartbeat detected. Okay, it seems that the signal itself looks good. We don't have any heartbeat left in our data, so it looks pretty clean. Also, the high-pass filtering seems to be good. Now let's look at the data itself, look at the analysis. So we just close this tab for now, and we go to the real-time channel analysis. So here on the left, you basically see the channels that you see also here. So you can also go into this part and select and deselect the channels over here. What we are interested in this setup is left and right. So we have two conditions. Condition 1, which was left tapping, and we have the condition 2, which is right tapping. So we can modify the names afterwards as well. And we are interested in the difference between these two tasks. So how did the participant perform overall, and do we see a different pattern? So we can first of all only show the event-related average of the time course that we are interested in. So now I only show left tapping, for example, which is here marked in red. And you can see that there's a clean signal. So as I said, we use the HPO and HP, so the HRF for the general linear model for the calculation, which is now shown here in the background. And this is our reference function, which we use for the GLM to compare our statistics to. If I want to see how good our statistics are, I can just define now this specific condition, for example, the tapping. Now I can look how my betas, so how strong the amplitude of this condition is. This is drawn here in the strengths and the color of the bars. So if I uncheck this, you can see it maybe a bit better. So the color and the strengths will define the value, but you can also see it here in the color and the strengths, in the color of the channel. So to do a statistical test, you can click on t-test. And now it will run a GLM based on the model that you see here and your data that is coming in. And what you can see is that there seems to be a significant channel here, this one, but also this side seems to be rather active. Now let's look at the other channel. So the other side, the right tapping. So we select only the plus here, meaning that we are interested in the right tapping condition. And what we see is that there's now the activity moved to the left side, also as we expected it. So now we can, for example, select the channel here. And as we can see that there's a clear pattern for the right tapping on this channel. Now, how can we verify otherwise that these channels seem to relate to this task? We can, for example, use the channel correlation over here. Channel correlation means that the channel that is selected, now this one, is correlated with all other channels, and the correlation value, which you see here in the table, is then highlighted based on here with this coloring. So the more red the color, the higher the correlation. And as you can see, the correlation is pretty high in areas which are close by. And if I go to the other side of the setup, I see a similar pattern. But what I can also see is that the pattern on the right side here seems to be stronger now for the right activity compared to the left activity. Then there's one more option here, which is the anti-correlation. This is nothing to do with the charts that we are seeing here and looking at. This is more an overall signal quality. So it checks if there is an anti-correlation of oxy and deoxy signal. And we see that there's a pretty high anti-correlation as expected, or as we want to have it for NIRs in these channels that are also our main interest. Okay. What Turbo Satori also allows you is to select multiple channels. So right now we only looked into one channel, but if you want, for example, want to see the difference, you can just click into the multi-selection mode, and then you can see two channels at the same time. Now, for example, I'm looking at this channel and this channel. As you can see here in these two time courses, that the second channel is much lower than the first one. Now, looking at the other condition, we basically see that it's the other way around. So now this one is in the top, so this shows a higher activity. So with this, we could nicely see that there is a difference between left and right. Now, to statistically evaluate this, we can also do a test. So we can check if there is a difference of the one side compared to the other. And I switch back to the single selection mode to see this a bit better. And here we see that there is a clear difference, so that the left tapping is stronger on the right hemisphere compared to the left hemisphere. And if I want to strengthen that, even that I combine it with the conjunction analysis, that I also check that it is really, really active, I can also define a second contrast and run a conjunction analysis, which then ensures that my condition is also active and not negative. So Turbo Satori allows you these basic statistics just within a few clicks, and you don't need to do any manual scripting or any definition of triggers or protocols. This is automatically read from the header. So as long as you provide header information or trigger information with your paradigm, Turbo Satori will be able to read this information. Okay, let's look at another paradigm. So here we have the example data set from NIRx. This data set is also available on our website, which you can just download and run. And as you can see, Turbo Satori reads the information which are present in the header directly and loads the topo layout, so the setup, as well as all the channel information. So that you just have to open this header file post hoc and can start the analysis. If you don't want to wait till everything is analyzed, you can go here in the top and just change the data frequency read to the right, and then you can see that it is now showing much faster. This should be shown fluently, but because of the streaming, you only see a few frames. But on your computer, it will be very fluent. Now you can go to the maximum to the right, and now it will just analyze the data as fast as possible, and will only show you the results at the end. So as soon as this is done, one will see that it will do a general linear model analysis now. And this GLM is a special one. So during the processing, there is a real-time GLM calculator, which I will just explain in the slides at the end. And at the end, completely at the end of the run, there will be a full GLM calculator to be sure that the statistics that you see here at the end now is really the full statistics. So having the full information in there. Now here we can do the same thing. So we have here again the same paradigm. So we have left-right tapping, but now we have many more channels. But we can still see a similar pattern looking at our contrast that we defined, condition 1 and 2 for left and right tapping. As you can see again, that this also shows the same pattern. Now currently we are only looking at oxygenated hemoglobin, but we can also switch or show in addition the deoxygenated. Here it is shown as blue and red, as you're familiar. But you can also show the HRF, so the model for the deoxy. And now you can zoom in and out and have a deeper look into this. Now, if you want to run the statistics on this, on the deoxy, you just switch from oxy to deoxy. And then the statistics is calculated only on the deoxy. And what you can see is that this has a much stronger effect in the deoxy signal, which can have multiple reasons, but it's interesting to look at it and maybe use this also as a decision to decide which type to use for neurofeedback or for BCI application. If you want to look at the total, you can just switch here to total, and then the whole calculation is done and total oxyhemoglobin. So looking at the thresholds here, these basically define the coloring. So if I only want to see which channels fulfill our statistical test, I can just scroll here down and basically see, okay, all the reds, they fulfill our statistics. You can do additional corrections, for example, the false discovery rate correction or Bonferroni correction to check for multiple comparisons. So if you change, for example, to the FDR correction, you see that the p-value is adjusted. So it was before in 0.05, and now it changed to 0.014. And this also showed that there were now much less channels. Here we now see that they are quite symmetric, but you can go even further to the Bonferroni, and then you see that we lost even one more channel. But here you can also see the p-value, which is adjusted accordingly. So with this, at the end of the run, you have a full GLM based on the data, which allows you to do or to make some decisions for the next ongoing runs. Below the thresholding, you also see that there is an option for averaging. So if you, for example, want to look at these channels combined, you can disable the single selection mode and select all these channels. Now you see all these signals. Now you click on Show Channel Average. And then you see the statistics for these. And if you only want to look at the channel, so now it is basically hidden in here because it's pretty much the same. So we can hide the error intervals and then you might see it. But if you really want to see it, you can click a second time and then you now see here in black and here in green the time course of the event related. And now it's marked in black as well in the background. With this, you are able to create a channel which is just the average of multiples, which can also be an option for later neurofeedback or BCI applications. And this is true for, again, for oxy, deoxy, and for total. So these changes the statistics then accordingly to these signals. If you look into the channel correlation, you can surely see that I didn't use too much. So if you look into the channel correlation, I think I loaded too many data sets, no problem. So we can just rerun the same run. I think this was the small one, so we go again to the big data set. Yes, so this is the big one. So I let it run through the end of the trial. And if you look at the channel correlation, you can see here now in this bigger setup that there is a different range of these channel correlations, which show you that there seems to be a clear pattern more in the central, which is also expected, and a lower pattern in the sides of the head. So you can just click these channels and then you see in the correlation value changed where the patterns are. I didn't talk about the display here in the top. This is a spectrogram showing basically the same statistics, just normalized to the maximum values. This you can use for if you have a good setup which is divided into different parts. For example, these left and right setup here. You can just select these correlations, and then you will see here in the top that there is a clear pattern between the one hemisphere and the other hemisphere. But this is just a different view onto these data, allowing to see the data without any thresholding, just looking at the signal themselves. So that you can see here the left-right is then shown here in these patterns. Okay. If you want to look at the time course, again, here in the bottom left, we have the overall time course. This is the time course of all channels that are available here. And this allows you to see if there are any spikes or any motion or bigger issues overall in all your data sets or in all your channels that you see. If I, for example, show the whole data set without the masking, you can see that there's a lot of noise and a lot of signal drop. And this would be also visible in case your data is not as good as it is over here. Okay. If you haven't provided this layout, you can also create it yourself and then load it using this view manager. So all these sources and detectors, so sources in red and detectors in green, can be freely adjusted. So you just have to enable the editing, and then you're able to just move them around. And you can also define new connections. So in this case, the setup looks pretty good, but you could, for example, add a connection to, for example, the node 5. So just right-click, add a connection with source 5. And then you would see, okay, there's now this connection added. This allows you freely to define whatever type of setup you want. And you can easily store them using the layout manager and just save the newly created setup. It is stored in a Satori layout file, which is a very basic text file. And this you can also modify yourself if you want to. If you haven't provided these information within NIRx, you can just create this layout yourself, store it into the same folder, and then just name it in the same way that the header is called. And then Turbo Satori will automatically load this layout for this data set. If it's not found and you start another time the run, it will basically just use the one that is available. So it will now remove this time course. Okay, let's look here at the top in the bar. We have different options here. In the analysis tab, we have basic options for the GLM, for the diagnostics, for SVM, and for channel subtraction. What we've seen till now is that the channels are presented here, and we see a specific pattern. Now, in the current literature, it's stated that for the GLM and for the best analysis, we should not use the filtered data, but we should use the oxygenated data itself without filtering. So this is also the default setting in the GLM parameters. But you can also use the fully processed data as you see it here for the GLM analysis. There you just have to check mark this little option here, and then you would see the GLM based on the data that is pre-processed here. Otherwise, you have some options to add confound predictors like linear trend, high-pass filters, heartbeat confound predictors. That means all the channels that have a heartbeat will be combined, and the mean signal of these channels will be used as a confound predictor. This is only a good option if you have enough channels, for example. But you can also filter the data so that you only include the heartbeat itself without the rest of the signal in these channels. Then another option is to have channel confound predictors. So if you have, for example, a specific channel that you know, okay, this will include noise, maybe not physiological, but some noise that you're not interested in, you can just type the channel source detector number here, and then just check mark this one, and then it will be added to the GLM. If you have short channels available, you can just check mark this option, and then it will automatically add the short channels into the GLM. It will automatically detect which short channels are available and will define them manually, automatically. In the href, you have the default SPM href settings, and in the contrast, you have some additional options which are not important right now. Okay. So to look how the GLM worked, we can basically show the whole time course, as you can see here. And then we can look at the GLM diagnostics. So we can show the predicted signal from the GLM, the residuals, and our confound predictors. So first start with the confound predictors. These are the predictors that we added, which should explain some low frequency fluctuations and drifts in our signal. If you have short channels, for example, you will see other confounds or other high frequency signals, for example. In this case, we only have these few. If you want to look at your predicted signal, you just click here, analysis, GLM, show predicted. What you see already is that this differs quite a lot to our to the signal that we see here. And this is because we filtered our data. If I would disable the filtering and would rerun the data set again, then I will see basically that the signal looks much more similar. Okay, let's run through. Yes, and now you see that the predicted signal here, the green time course, represents what the model estimated. And you can see here for this channel, which is this part, you can clearly see that there is a higher activity or a higher peak for the conditions for the right tapping. And this is also shown here for the model. If you want to look at the residuals, you can just go for GLM and show residuals. So this is all the data that is not explained by your model. And there shouldn't be that much correlation left in your data, because that would be a problem for the statistics. Now, if you want to look at the overall fit of your data, you can just go to each channel and just check how the overall fit of your data is, of your model is compared to your data. So in this case, we have the t-test again. here, for example, and if you hover above this value, you see that the R squared for oxy, deoxy, and total separately. So if I show the deoxy here, for example, which is now marked in blue, and you see here as well in blue, you would also see here for the predicted signal now the deoxy signal. And here you can see a very clean signal, and you also see that for the deoxy you only have a decrease for the second condition, which was right tapping. Now these procedures allow you basic inspection of your statistics, of your analysis pipeline, and can be very easily used to verify that your data is properly recorded. So in summary, you have right away a heartbeat detection, which is also shown here on the side. So as soon as you see a little icon, that means that your heartbeat is there. If you don't know which channel number source detector pair is, you can just hover on top of it and then you see the channel number. If you want to look at your more detail at your signal, you can also go to the frequency tab and then look at the frequency spectrogram. So here, for example, we see that there's that the majority of the signal is in this part. If we don't run the low pass filtering and then do again the frequency information, this is also updated in real time. Then we see that there is a clear pattern here, which evolves, and we should also see a heartbeat part, which is visible here in this part of the signal. And then here in the bottom you have a log tab, which writes down all the information that is important for the processing. Okay. Some more information are available here in the analysis. So we have also a support vector machine or a multi-class or multi-channel pattern analysis. And for this, I want to thank first Bettina Sorger for providing this data set. In this data set, we have two tasks, motor imagery and mental rotation. And this is a very specific setup of the channels. So you can define the setup as you want to, and then just load them into Turbo Satori. I forgot to enable again the high pass filtering, so I shortly stop this one and rerun it. Okay. Yes, and then I can fast forward again the recording. Okay, for the classification, we basically try to create a classifier which tries to help us to separate, in this case, two conditions. So the first condition is the motor imagery, and the second one is the mental drawing. So the motor imagery is a pretty strong pattern which we see here, but usually it's a lot of effort to create classifiers and to use them. Here in Turbo Satori, you have a specific tab which is called SVM training. So you can just go to this tab, and as soon as you've finished this analysis, it will automatically fill in this information. Now, I don't want to go into too much detail here. I just want to show you how it basically would work. So the most important is that you extract from your data that you see here all the periods that were used to create the task. This is in this case the data 2 seconds before the onset, so this part, and 10 seconds after the onset. So it's basically the part in here. If you press go, it will automatically extract this information from the trials and will store them in a separate file. To create the classifier, you now need to merge this data from the classification and put this into a matrix so that it's possible for the classifier to create the support vector. Now this is the data that shows that there is a clear difference between the first condition here in the top and the second condition. Now to train a classifier, you only need to click on train, and then you're basically done. What you can see in the test classification is that we reached an 80% accuracy with our classifier, meaning that 80% of our data could be classified correctly. That is okay-ish, but we maybe want to improve this still a bit. So our classifier now with a value of 1 here means that it would accept some misfit classification. It can be a bit stronger, for example 10, saying that the classifier should really be correct. If you then train again, we see here in the classification tab that we now reach 100%. I hope you can read it, meaning that in this case we managed to reach the full classification accuracy. Now this value, if the value is 1, it means that it will be more generalized, so that more data sets would have a good accuracy. With the value of 10, it is quite strict, saying that all the data must fulfill the requirements that it's either imagery or somewhat imagery or mental rotation. But just here for this example, I now use the value 10. Okay, let's load so this was the training session. So the participant performed the tasks 2 times. Now we load basically a testing session. So the participant is now really performing the task a second time, and we try to use our classifier to predict what we have done. So first of all, our classifier is now available, so we can go to real-time classification and just load our classifier, which is this one. Then we can press predict, and now the classification is waiting for data, meaning that for the real time, you would now connect, for example. Here we now load the testing data set. Okay, now the data is coming in, and because we said that we want to use the trial duration, the classifier will only predict as soon as the trial is over. Okay, we can zoom in a bit and look at the event coming in. I can here increase the speed a bit in the top. Okay, and now you can see the task started here, and now the classification will start after the 10-second period onset. So and now you see this is for the time point, we get a predicted value. So a value which is positive means it's the first condition, motor imagery, which is also true. So for the first trial, this was correct. This is the second trial. We also get a positive value, which also means that we classify this one as motor imagery, which is also correct. For the third trial, we see the same, just increase the speed a bit. Also see a positive value, also meaning it's the second condition. Okay. And again, another motor imagery, let's see if it's classified again. Yes, this was again correctly. Now it starts the second condition, mental rotation, and we now see, okay, now we get a negative value, meaning that it's the condition 2. In the second trial again, a -1, and again, negative values. So with these easy steps, we basically created a classifier only based on 2 data sets, one a training data set and now a testing data set, which allows us to classify these 2 mental tasks. And in total, you would need these 2 runs. If you have more runs and more participants, you can also create a generalized or more general support vector machine. But this is within a few clicks, you're able to create this classifier and do some predictions. Okay, some information about the BCI and neurofeedback. So we have a BCI neurofeedback dialog, which allows you to create out of this time course that you see here a neurofeedback signal. You have a lot of different options to create or to display the thermometer. And this is updated now for each frame. And you can also export this information as numerical values so that you can, for example, display this with other tools, or you can also export the images and then show them, for example, using presentation or any other tool that you want to use. In the plugins menu, you can create your own plugins, meaning that you can add additional features to the software. These plugins will be loaded as in a small window and will allow you to access the data that is used in Turbo Satori. The plugins are written in C++ and usually are only interesting for programmers, for example. In the view options, you can show and hide the axis, for example, so that you see a bit more information. But you can also switch from OpenGL drawing to CPU-based rendering. This is, for example, important if you work remotely or if you don't have a proper external or a proper graphics card. The dark mode of the software, so showing this dark interface, is the default, but you can also disable it and have the normal interface in a white view form. If you need help information, you can just go to help and open the user's guide. The user's guide allows you to search. So for example, if you want to have information about the contrast, you can just type here contrast, and then you click on the contrast window and it will show you the information about the contrast window. Another way how you can find help is just by hovering on top of the interest or in the information that you need. For example, motion correction, it tells you which paper it is. The SSR correction, the same thing. So some of the information are present directly on this on the spot where you need it. Then we also have release notes. These are important for each version, so you can see what changed in the version, and you can go back and see even what's changed in the subversion. And this you should inspect every time there's a new Turbo Satori version, what have changed and what features are come and which bugs are fixed and so on and so forth. So these you find as well here in help, the release notes. Okay, this is it for now for the interface itself. I will now switch to some slides. So I hope it was not too extensive till now, but we still have some time after the webinar for some questions, I think. So Turbo Satori has a clear processing workflow. At first, you have the continuous wave NIRs data as raw data that Turbo Satori reads in via the LSL stream. So you have to set this option in NIRstar so that Turbo Satori can see NIRstar. Then it calculates the concentration changes using the modified Beer-Lambert law. Afterwards, we perform the processing, the pre-processing, followed by the statistical or the overall analysis. The pre-processing consists of linear detrending, filtering, so finite impulse responses and infinite impulse responses. We have motion correction, SSR correction, and the channel subtraction. In the analysis part, we have the general linear model, correlation analysis, anti-correlation analysis, support vector machines, brain-computer interfaces, and neurofeedback. Important is that for the pre-processing, these steps are performed after each other. So first the linear detrending is applied, then the filtering, then the motion correction, then SSR and channel, if these are selected. So the order is not possible to change. This will come hopefully in a later update of the software, but right now this is the order of the pre-processing. Okay, let's look into a bit more detail of the filtering. As you saw on the right of Turbo Satori, there are here these filtering options. So as a default, we have the moving average, but you can also select different options. For example, the butterburst filter, which is very often used in fNIRS research. There are a lot of filters. for example, the moving average, but also the exponential moving average, which is also very often used in the data sets. They can be combined if needed, but they can also treat it as separately. In the order and the cutoff, you can define which order the Butterworth filter, for example, should have. But you should be cautious not to have a too high order to not cause too much delay in your data. For moving average, there's even a limitation that you can only have order 3, because otherwise you would introduce a higher lag or a delay in your data, which you don't want to have. Okay, some more details about the GLM, because I think this is a very important feature in Turbo Satori. For the statistical analysis, as you have seen in the data, so we basically have our model, and with the information that we provide, so as you can see here in our design matrix, the more data will be explained. So if you only, for example, provide one line within our design matrix, we will only have one predicted time or a flat line. If you provide the information of one task, for example, we will get an explained data for this one task, for example, but not for the other. And if you would add another task, we would basically predict the two time courses and could also see differences. Now this is done, this design matrix is created automatically based on the triggers, but you can also provide protocol information if you don't have the triggers at hand. Now combining these, the design matrix, which is our model, together with the residuals forms our time course, the fMRI, or in our case, the fNIRS signal. Now, standard GLM analysis consists of the model, the beta, the estimated beta values, and our error terms. Now, since we use this a lot for fMRI, this is also true for fNIRS. And the most important part is that the GLM, fitting the GLM is the same as finding the estimates of the betas that minimize our sum of squares of the error values. Now this is standard statistics, but we have some limitations for the real-time analysis. And that means that we have to calculate all these statistics within the repetition, or within the time of the recording. Now, the design matrix that we see is the same for all channels. And this allows us to basically create this term, which is a computational big effort to create, once for all channels. And this allows us to calculate the statistics much faster. And for NIRs, the more channels you have, the better this term is. And the more important it is to calculate this once for all the channels itself. Now what we do in addition is, after we have calculated the first GLM, we do the parallel processing using separate threads to calculate the T statistics. And this is necessary because we have a high autocorrelation in our data, because the fNIRS data is sampled so highly with 10 Hertz, for example. We have to take care that the time course which we use is not, or the residuals in our time course is not autocorrelated. Now, in the data that we first get, so our first GLM approach, we have to use some more steps. At first, we have to determine the AR model, so which order we need to use to correct our signal. And this we do using the Bayesian information criteria. Afterwards, we need to estimate the parameters using, in our case, the Burke's methods, the Burke's maximum entropy method. Then we correct the NIRS data and the design matrix using the estimated parameters. And then after we've done this, we rerun the GLM. So this is very time consuming, and this is why we run it in separate threads. So our T statistics is not updated in real time, but as soon as the thread is finished with the analysis, which is with good computers pretty fast, but it takes some time. So this is not available for each frame, and not in real time, but the beta statistics, which is the basis for this in the first place, which is not affected by the autocorrelation, this is available in real time, and this you can also access. Okay. So this was the short part of the GLM. Now looking at a bit more important parts for the BCI and neurofeedback. So how does Turbo Satori combine into the real-time fNIRS and BCI setup? So in NIRstar, we acquire the data, or later Aurora, and we need a TCP connection to Turbo Satori. And this is done using the LSL streaming layer. This can be done via Wi-Fi or a direct cable connection. So Wi-Fi is also no problem, and we tested this as well. Now, how do you access the data in Turbo Satori? We have different or multiple examples how to access the data. There are connections from Experiment or Brainstorm, which are presentation tools, but there are also interfaces for MATLAB, Python, and C++. So if you're, for example, a MATLAB user, you can just download example scripts from our website and just access, for example, the time course of a specific channel from Turbo Satori. And this will be only one short command. Now, after you've provided the stimulus information onto a different application or a different screen on Turbo Satori, for example, you can show the stimulus to the participant, and you can as well trigger the information to the NIRstar, or even trigger the information from NIRstar itself. And since this trigger information is then sent to Turbo Satori again, we have a closed loop setup which provides the information from all parts to each other. Now, Turbo Satori has the standard neurofeedback display that you know, but we also provide some BCI demos, which you can also download from our support websites. Some examples are here shown on the right. And with the BCI and neurofeedback, you are able to monitor the HB and HBO changes online. And with the spatial resolution of NIRs, you can really provide content-specific feedback to the participant. And this allows subjects to learn to influence their own brain activity from the circumscribed brain areas. Now, for example, we use the motor imagery areas, but you can also use prefrontal cortex or other areas of interest. The software used here is a standalone tool which automatically connects to NIRs, to Turbo Satori. So you don't need to set any information, you just start the application and connect to the software. If there's interest, I can show you how this works as well. Some little future outlook. So we will implement some view modes so that you don't have to just change the modes manually, but that you have really specific view modes, for example, for the topo layout, for single time courses, or for multi-channels. Then we will add multi-class classification in the SVM. We will have more examples for BCI and neurofeedback setups. And we will have as well 3D visualizations in the software, but this will be in a later stage. The data import and export is currently the header format, but we will also support the .NIRS format soon. And if there's a new NIRS standard, then we will also support this one. And the cross-platform compatibility is also on the list of features. Now, one thing that I want to also point out is our offline analysis software Satori, which is currently in development. And this allows you to process your data, have multi-session analysis, group comparisons, full GLM as well, MVPA, connectivity analysis, and advanced visualizations. And this software is completely opt-in analysis and will be available this year as well, which will give you the same user experience that you already see with Turbo Satori, where you don't need to have any programming experience and can just use the tools as they are inbuilt. Okay, how do you get support for the software? Basically, there are ways to access information. One is our support website at support@braininnovation.com. You can also email us at support@braininnovation.com, or use our learning material, which is available on the support website. And further information is also available on our main website. So that's it for now. I hope there are some questions. And thank you for your attention.
Thank you very much. This was great. From the registration time, we have one question, but not related to Turbo Satori. They are trying to learn features of Turbo Satori to make a purchase decision. I hope they know enough now, but if you need some more information, please write to us. We'll be happy to talk about it or tell you something more. From the chat, we don't have any questions, but we still have a few minutes. I believe if you have any questions, you can type in. We will be happy to discuss it. We might have one question. Okay.
Okay, so we hope you were connected. Somebody may have lost their connection. Are you able to see from the questions from Stanford? Is there an API available to use some of these individual functions outside of the main user interface?
So the API is only gives you access to the to the data itself. We will provide over time also MATLAB functions which basically reproduce the results that we have in Turbo Satori. So if you're interested in a specific analysis step, then you can contact us and we can provide you with some information how to do this in MATLAB yourself if you want to.
Another question, also from the same user. So is it correct to start a single subject level while the offline analysis software will be also for group analysis?
Yes, that is correct. So Turbo Satori is really a real-time application for similar subjects, and the Satori will be an offline analysis toolbox for multi-subject analysis completely. Yeah.
There is also our friend Leo, our colleague Leo, who I learned that very much. Thank you, Leo. Claire, I'm not sure I understand.
Is there any ML involved? I believe she means machine learning.
Yes.
For data.
For data analysis, she doesn't turn machine learning involved for data analysis. So maybe while we can go to the next question, Claire, if you please don't mind clarifying, you can just post another question. In the meanwhile,
we have one more. I have a data set recorded in NIRx. Can you first process these data sets in Turbo Satori? CMU mode for training, and would that require specific script to convert file format, or HDR file is enough?
So currently the HDR file is enough, and it tries to search automatically for all the information that it can grab from the HDR files. But as I said, in the future we will also support .NIRs, so that you can also use .NIRs recorded information to rerun in the simul mode for training. Exactly. This is also the main intention for the simul mode, that you have the possibility to get familiar with the software without needing to connect all the time to your to NIRs, for example. Regarding the
hardware section, are you there or?
No, I'm one higher. So the machine learning, so the support vector machines is the only machine learning tool that we have right now. So if you use the support vector machines, then yes, the other tools are not using machine learning at the moment.
Mm-hmm. And the last question for the moment is, what algorithm is behind the online hardware detection?
So for the hardware detection, we developed basically a method which is described here in the user's guide as well. Let's see if I can find it easily. No. Let's see, pre-processing. See if you can see it. If you find it before me, then can't see it at the moment. No, but so the method itself is based on the frequency of the data. So it does a frequency analysis of the channel, and in the channel where it finds a specific heartbeat frequency, which lies in the range of 0.7 to 2 hertz, if I'm not mistaken, then it will show the heartbeat symbol. So meaning that if there's any peak or any high difference compared to the filtered series which is before it, then it will be used as a heartbeat.
Mm-hmm.
Okay, that seems to be pretty much
Yeah, clear. Thanks you for presentation.
And Kate, we hope you managed to get back.
Yeah, again, if you have any further questions, please write to us. You can write to Michael himself. We'll be happy to answer any questions you have. This will be uploaded to our support site. So if you missed anything, you can go to our support site and have a look again. So thank you very much, Michael.
Yes, thank you everyone.
See you next time. Bye-bye.